Now that we've covered the digestive system and you all have an in-depth understanding of how the digestive system transforms food into nutrient molecules in the body, you're now ready to learn about how the body converts these nutrients into fuel that we use on a daily basis. When you guys become healthcare professionals, it's essential that you understand all aspects of good nutrition and how the nutrients are converted into energy. This will allow you to effectively advise your patients on different dietary choices that will enable their bodies to operate at peak performance levels. To make proper dietary recommendations, you all need to know about the different nutrients that the body requires to function normally, including the macronutrients, which you can see here. The macronutrients include the carbohydrates, the lipids or fats, and the proteins. Each of these major nutrients plays a different role within the body, and excesses or deficits of these nutrients can have detrimental effects on a patient's overall health. For example, if there is an excessive consumption of proteins, this can lead to kidney stones, while patients who do not consume enough protein may develop anemia. Counseling your patients on the recommended daily allowance of essential nutrients may help you to prevent these conditions from even occurring at all in your patients. A thorough understanding of the impact of various nutrients on the body will enable you to educate your patients on leading healthy and nutritionally balanced lives. So let's jump right into this and start with some simple definitions that you all should know. First, we'll talk about what nutrients are. Nutrients are substances in food that are needed for growth, maintenance, and repair. Most nutrients are used for metabolic fuel, but some are used for cellular structures and molecular synthesis. And then we've briefly talked about the macronutrients, and they include the carbohydrates, the proteins, and the fats. And we're going to dive a little bit deeper into each one of these food groups as they make up the majority of nutrients that we ingest on a daily basis. So we've mentioned that the macronutrients are the carbohydrates, the lipids, and fats. There's also subcategories of micronutrients as well as essential nutrients. So the micronutrients they're required, but they are only required in small amounts. And micronutrients include vitamins and minerals. And water is also required for our body, as it makes up approximately 90% of our body. So water is technically a nutrient as well. And we have the essential nutrients, which are nutrients that must be eaten because the body cannot synthesize these from other nutrients. And there are about 45 to 50 of these essential nutrients that we need to take in on a daily basis to maintain healthy status. Non-essential nutrients are also very important to regulating and balancing homeostasis. But there's not enough of the non-essential nutrients available. The liver can usually compensate for this by converting another nutrient into one that is needed. And we measure our energy usage in kilocalories or kcals. And a calorie is the amount of heat that's needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. So 1 dietary calorie equals 1 kilocalorie. This picture here is known as the USDA MyPlate, and this is a general guideline of the 5 major food groups. And for basic dietary purposes and principles, you should only eat what you need to eat. And it's better to eat less overall than to consume food in massive amounts. If you are going to eat more food from some of these food groups, it's better to consume more of the fruits and vegetables and whole grains and try to avoid the junk food. So now we're going to dive deeper into each one of the macronutrients, and we're going to start by talking about carbohydrates. So carbohydrates are derived primarily from plants, such as starch that's found in grains and vegetables. Carbohydrates could also be sugars, both mono and disaccharides, which are found in fruits, sugar cane, sugar beets, honey, and milk, so on. Carbohydrates also include soluble and insoluble fibers. The soluble fiber can be found from what's known as pectin in apples and citrus fruits, And soluble fiber is really good for reducing blood cholesterol levels. And the insoluble fiber can be found in the cellulose component of vegetables. There's a small amount of carbohydrates in milk and sugar, and even some in meats. But what our body uses carbohydrates for mainly is for fuel, and it uses them in the form of glucose. So most of our cells of our body need to use adenosine triphosphate, or ATP, to fuel themselves. So excess glucose is converted to glycogen or fat, and then it can be stored for later use as well. Fructose and galactose are converted to glucose by the liver before entering the circulation. And it's recommended that you take about 45 to 65% of your total calories from carbohydrates. And this should consist mostly of complex carbohydrates coming from whole grains and vegetables. You should really limit your simple carbohydrate intake. And high amounts of sugars can lead to obesity as well as other nutritional deficiencies. A typical American diet is approximately 46% carbohydrates, and that includes eating rice and pasta and breads with almost every meal. And this tends to be relatively inexpensive, so higher percentages of carbohydrate consumption are seen in low income groups and those of low socioeconomic status. And you can see on this picture here the problems that can result from the excess consumption and not consuming enough carbohydrates in your daily diet. Many of you may have been told that fats are bad to consume. Well, that's not exactly true, because fats are an essential component of a healthy, well-balanced diet. So most of the fats that we consume come from triglycerides. These are neutral fats. And triglycerides are found in both saturated and unsaturated fats. It's better for your body to consume more unsaturated fats versus saturated fats. And the unsaturated fats can be found in different types of seeds, nuts, olive oil, and most vegetable oils. Where the saturated fats are coming from meat, the dairy products, tropical oils, or hydrogenated oils such as trans fats. The liver can convert some fatty acids into others, but the essential fatty acids such as linoleic and linolenic acid are found in most oils, and these must be eaten, as we're going to talk about some of the essential amino acids later in this lecture and explain why they're so important to consume. So what do we even need fats for in our body? Many of us, well, all of us have some part of our body that consists of adipose tissue. You can't have 0% body fat, or that would just not be functional to have. The adipose tissue is essential as it offers protection, insulation, and long-term fuel storage for us. So the phospholipids are, for example, essential in myelin sheaths and helping our cell membranes maintain their integrity. Cholesterol, which is another type of lipid, helps to stabilize the membranes, and it's also a precursor of bile salts and steroid hormones, which help us in anabolic and different metabolic processes, such as building muscle. We also use lipids in the form of prostaglandins, and this helps to contract the smooth muscles. It helps also to control blood pressure as well as regulate the inflammatory response. And lipids also help to absorb fat-soluble vitamins that are essential to maintaining and regulating homeostatic balance. And lipids are the major fuel of hepatocytes. Remember, hepatocytes are the liver cells, and they're also a major fuel for our skeletal muscle. So the American Heart Association recommends that fats are no more than 30% of your total caloric intake daily. Saturated fat should only be 10% or less of the total fat intake. And cholesterol, so there's two types of cholesterol. There's HDL, high density lipoprotein, and LDL, low density lipoprotein. So HDL is the good type of cholesterol. So it's okay to have a little bit more HDL than to have a little bit more LDL based on recommended daily values and what the AHA and the FDA suggests. So for cholesterol, you should not consume more than 300 milligrams per day, and that's approximately eating 1.5 egg yolks. So most of the protein in an egg is found in the egg white, so not the egg yolk. And the egg yolk is high in cholesterol, so don't eat too many of those on a daily basis. And the main goal is to keep systemic cholesterol below 200 milligrams per deciliter. Now let's talk about proteins. Proteins can come from many sources, including animal products such as eggs, milk, fish, and animal meat. Protein can also come from soybeans, and all of the protein sources that I just mentioned are considered complete proteins, as they contain all the needed essential amino acids. So, as I just said, proteins can come from other sources than those I just listed. Proteins can also come from legumes, nuts, and cereals. However, these are known as incomplete proteins because they lack some essential amino acids. Legumes and cereal grains together contain all the essential amino acids that you need. So what do we use proteins for in the body? Well, first of all, we use them for structural materials, such as keratin, which helps maintain our skin integrity. Collagen and elastin needs protein, as that makes up the majority of our connective tissue. And our muscles need it to synthesize and build and repair after we use them. So there's 3 factors that help determine whether amino acids are used to synthesize proteins or whether we're going to burn these amino acids as fuels. So the first is known as the all or none rule. So the all or none rule states that all amino acids needed must be present for protein synthesis to occur. If not all of them are present, then amino acids are going to be used for energy. The second rule is adequacy of caloric intake. So protein is used as fuel if there's insufficient carbohydrate or fat available. And the third use of protein is for hormonal controls. Protein helps regulate different anabolic hormones, such as growth hormone and the sex hormones, estrogen and testosterone. And it helps to accelerate protein synthesis as well as overall growth. And the adrenal glucocorticoids, which are released during the stress response, they promote protein breakdown and conversion of amino acids into glucose. And protein is also essential for nitrogen balance. You can have either a positive or a negative nitrogen balance. And these balances are based on whether or not the homeostatic state and rate of protein synthesis equals the rate of breakdown and loss. So how much protein we're synthesizing should be equal to the rate that we're breaking down and losing it to maintain a equal nitrogen balance. So if the synthesis exceeds the breakdown, and positive nitrogen balance is very normal in children and pregnant women, and also when you're undergoing tissue repair. So if you have a positive nitrogen balance, this is when the synthesis is exceeding the breakdown. And if you have a negative nitrogen balance, the breakdown is exceeding the synthesis of protein. So what could happen here is, or the things that could cause this are stress, burns, infection, injury, poor dietary protein consumption, and when people enter states of starvation. So how much protein do you need on a daily basis? Well, this is different for people of different ages, sizes, people that have different metabolic rates, and different nitrogen balances. So the general rule of thumb is to take in 0.8 grams of protein per kilogram of body weight. And the American diet typically provides more than what is actually needed. Now let's talk about vitamins. And vitamins can be classified into two main classes based on their solubility. Whether vitamins are water soluble or whether vitamins are fat soluble will determine what class they're classified in. So you can see on the table here, this is a list of all the water soluble vitamins. Just remember that B and C are water soluble. So as you can see here, there are many different types of B vitamins, and we may not even know all of the B vitamins that exist in the body currently. I don't really need you to know each one of these B vitamins individually. Just know where they come from as major dietary sources and really focus on vitamin B12. So B12 absorption requires intrinsic factor. Really want you to know B12 is associated with intrinsic factor. And B12 really helps to regulate the maturation of our red blood cells, as we've talked about in the blood lectures. Water-soluble vitamins are not typically stored in the body, and if we don't use them within 1 hour of consumption, they're typically excreted. So now you can see a chart that depicts the fat-soluble vitamins. So these include vitamins A, D, E, and K, which are absorbed in our body with lipid digestion products. And each one of these vitamins can be stored long-term in our body except for vitamin K. And excessive consumption of any of these vitamins can cause long-term health problems. So again, you don't need to know all of the major functions or all the conditions that may result. I just want you to be able to determine which vitamins are fat soluble. Again, A, D, E, and K are fat soluble versus the ones that are water soluble. So remember, the B and C vitamins are the water soluble vitamins. In our diet, we consume a broad array of minerals on a daily basis. However, there's only 7 main minerals that are required in moderate amounts. The rest are only required in trace amounts, and we're going to talk about that on the next slide. The 7 minerals that are required in moderate amounts are depicted here on this chart for you, and they include calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And these minerals work with other nutrients in our body to ensure that our body functions properly. And both the uptake and the excretion of these minerals has to be in a well-balanced fashion in order to prevent toxic overload from occurring. So let's go over a couple uses of these minerals in our body. So calcium and phosphorus and the magnesium salts, they all work together to harden and strengthen our bones. Iron is essential for oxygen binding to hemoglobin. So remember, when an hemoglobin molecule is fully saturated, it will have 4 oxygen molecules that are bound to it. And without iron present, oxygen is not going to be able to bind, and our hemoglobin is not going to be able to transport oxygen throughout our bloodstream, and that's going to be very bad for the body. Sodium and chloride, that makes up the salt, and they're major electrolytes in our blood. And if we don't have sodium and chloride, the key electrolytes, as many of you probably have experienced from exercising intensely, you may get a muscle cramp. And in addition, if you're not consuming enough salt, you may have an overall reduced appetite. So be sure that in your daily dietary regimen that you're getting at least, or if not greater than 200 milligrams per day of each one of these essential minerals. And an easy way to do that is to take a good multivitamin. This chart here shows you a whole list of other minerals that we take in on a daily basis. However, we don't need to consume more than 200 milligrams of these particular minerals, and we only need trace amounts. However, these minerals are still important to consume, and again, they can be easily taken in by taking a daily multivitamin. If you look at all the way over on the right-hand side of the screen, you're going to see some symptoms of deficiency. And you can go through and look at what happens if you don't intake enough of each one of these minerals. I'm not going to test specifically on any one of these mineral deficiencies. However, if there is a particular question that's going to be asked, I'm going to mention that later on in the lecture. When we talk about metabolism, metabolism includes the sum of all biochemical reactions inside a living cell involving nutrients. And we also have what's called anabolism and catabolism. So think of an anabolic steroid, and think of famous athletes or even the governor of California who is admitted to using anabolic steroids. Anabolism refers to building things up. So this is synthesizing large molecules from small ones. For example, taking small amino acids and building them into proteins. On the opposite end of the spectrum is catabolism. And catabolism refers to the hydrolysis, or using water to break down complex structures into simpler ones. So an example of catabolism would be the breakdown of proteins into amino acids. So again, anabolism is taking amino acids and building them into proteins, and catabolism is the opposite, breaking the proteins down into a simpler form, such as amino acids. So we're going to talk a little bit about the different cycles that help regulate cellular respiration and different phosphorylation processes. We're going to talk about glycolysis and gluconeogenesis, how glucose and glycogen are broken down and how they're also built back up and how they're formed. So cellular respiration is the catabolic breakdown of fuel where the energy from food is captured to form adenosine triphosphate, or ATP, in our cells. And the whole goal of cellular respiration is to trap chemical energy in ATP. And please note that energy can also be stored in glycogen and fats, which can be broken down later if we need that for later use. There's a lot of post-translational modifications that can happen in the metabolic processes, such as phosphorylation. What happens in phosphorylation is enzymes shift high-energy phosphate groups of ATP to other molecules. And the phosphorylated molecules then become activated to perform different cellular functions. So you can see here there's three main stages in processing nutrients. Stage one involves digestion, absorption, and transport to the tissues. So we've talked about all three of those components in our digestive lecture series. Stage two consists of cellular processing, and please note that cellular processing usually occurs mostly in the cytoplasm. And cellular processing includes the synthesis of lipids, proteins, and glycogen, and cellular processing also includes catabolism, such as glycolysis. So glyco is glycogen, lysis, the breakdown of glycogen. That's what glycolysis is. And we're going to talk about glycolysis, of how glycogen is broken down into pyruvic acid and acetyl-CoA, and how those play an essential role in the tricarboxylic acid cycle, or the TCA cycle. And the TCA cycle is also known as the citric acid cycle as well. And stage three, we have oxidative breakdown of intermediates into carbon dioxide, water, and ATP. And this stage mainly occurs in the mitochondria. So cellular respiration as a whole consists of glycolysis of stage 2 and all of stage 3. So before we dive into these chemical pathways, I need you all to understand some general terminology. And we're going to talk about oxidation versus oxidation reduction reactions. So when something is oxidized and it's undergoing an oxidation reaction, what's happening is there's a gain of oxygen or a loss of hydrogen atoms, and we lose hydrogen as well as the electrons that are bound to them. In the redox reactions or the oxidation reduction reactions, the oxidized substances will lose electrons as well as energy. And if something is reduced, it's going to gain electrons and gain energy. And I know those may sound backwards, but that's just something that you have to really take into consideration and memorize. So oxidation, we're losing electrons and we're losing energy. When we're reducing something, we're gaining electrons and we're gaining energy. So now we're going to talk about ATP synthesis. And there are two main mechanisms that are used to make ATP from captured energy that is liberated during cellular respiration. And these two mechanisms are substrate level phosphorylation and oxidative phosphorylation. Let's first talk about substrate level phosphorylation. And what happens here is there's a high energy phosphate group or groups that are directly transferred from different phosphorylated substances to ADP. And this occurs twice in glycolysis and once in the Krebs cycle. And the necessary enzymes are in the cytosol for glycolysis and in the mitochondria for the Krebs cycle. Oxidative phosphorylation is a little more complicated process than substrate level phosphorylation. However, this is the process that produces most of the ATP. And this is known as a chemiosmotic process, as what's happening here is there's movement of different substances across membranes to form different chemical reactions. So ATP synthase uses the energy of the proton gradient to bind the phosphate groups to ADP. And please note, this only occurs in the mitochondrial matrix. You can see here the chemical equation for cellular respiration. So when glucose enters a cell, it's phosphorylated to become glucose 6-phosphate. Most cells lack enzymes for the reverse reaction, so glucose becomes trapped inside the cells. Only the cells in the intestine, the kidney, and the liver can reverse this reaction and release glucose. And as this enzyme reaction cannot be reversed most of the time, this keeps the intracellular glucose concentration low, which ensures continued glucose entry. So let's break down this chemical equation a little bit more. So glucose and oxygen will yield water, carbon dioxide, and ATP. And heat's given off in the reaction. So you see all these numbers and all this different inputs and outputs that are produced here. So you can think about this in a really simple fashion. So glucose, that's our energy source. So our energy source can come from lots of places, especially our food. So we consume food, we're consuming glucose. The next step is oxygen. So you can think of this whole process as running. So we need fuel to run. So we need to consume food to run. And then what do we do as we run? We breathe in oxygen. So that's the left side of the reaction. And then what happens as we run and as we accelerate? We sweat, so we're losing water, or we're producing water. And we're breathing out. That's our carbon dioxide. And in the process, we're dissipating heat, and we're using energy in the form of ATP. And that's a simple way to remember that glucose plus oxygen will yield water, carbon dioxide, and ATP. And there are 32 ATP produced per round of cellular respiration. And now let's go down to the bottom bullet point. So complete glucose catabolism, or the complete breakdown of glucose, requires 3 pathways, and we're going to dive into each one of these pathways in a little more depth. So the first is glycolysis, the breakdown of glycogen. The Krebs cycle, also known as the TCA cycle or the citric acid cycle, and the electron transport chain and oxidative phosphorylation. So again, we're going to talk about each one of these a little more in depth in the upcoming slides. So seen here is the whole process of glycolysis, or the breakdown of glycogen. There's going to be a lot of information presented here, so you may have to replay this slide several times to ensure your complete understanding. So glycolysis can be broken down into three main phases. And let's just go from the top and go down to the bottom. So phase one, sugar activation. What's happening here is glucose is being phosphorylated by adenosine triphosphate to produce fructose 6 bisphosphate. It is then phosphorylated again by a second ATP, which results in fructose 1,6 bisphosphate to form. And this phase is referred to as the energy investment phase because there has to be an input of energy in order for this phase to be initiated. So in this phase, we're using up 2 ATP. However, these are going to be recouped later. And these 2 ATP are essential to provide the activation energy that's needed to start the pathway. And they act as the primer to the glycolytic enzyme pathway. So let's move down to phase two. What's happening in phase two is fructose 1,6 bisphosphate is being split into 2 3-carbon fragments. And the fragments can interconvert into one of 2 different isomers. They can either become dihydroxyacetone phosphate, or they can become glyceraldehyde 3-phosphate. And then in phase 3, there's actually 6 steps involved with 2 major events. And phase 3 is known as the sugar oxidation and ATP formation stage. So what's happening here is each 3-carbon fragment is being oxidized by the removal of a pair of hydrogen atoms, which are being picked up by NAD. And this forms a reduced complex of NADH plus a hydrogen ion. The hydrogen ions help to carry a portion of glucose's energy. And the inorganic phosphate groups are being attached to each oxidized fragment. So cleavage of these phosphate groups from both fragments will result in the formation of 2-pyruvic acid and the production of 4 ATPs by substrate level phosphorylation. So in glycolysis, although 4 total ATPs are made, the 2 ATPs that were needed to initially prime the system and get the system going in phase 1 must be subtracted. So let's talk about the final products. So we're going to have a net gain of only 2 ATP because, again, we had to use the 2 ATPs to prime the system to get the system going. We're going to have 2 pyruvic acids and 2 reduced NAD compounds. So for glycolysis to continue, more NAD must be present to accept more hydrogen ions. However, the supply of NAD is limited. NADH must donate its accepted hydrogen atoms to become NAD again in order to be free and to have the capability to pick up more hydrogen so glycolysis can continue. So if oxygen is present, NADH will transfer its hydrogen to proteins in the electron transport chain. We're going to talk about the electron transport chain in a little bit, and for now just know that the electron transport chain occurs in the mitochondria. If there's no oxygen present, then NADH is going to give the hydrogen atoms back to pyruvic acid, which will reduce it into lactic acid. And so what happens to the lactic acid? Well, some of it may leave the cell and be picked up by the liver, which can convert it back into glucose 6-phosphate, while other lactic acid molecules can be oxidized back to pyruvic acid when oxygen becomes available. And then that allows it to enter the aerobic pathways. So if we have any type of prolonged anaerobic metabolic events happening, this can lead to different acid-base problems within our body. And glycolysis results faster ATP production than aerobic respiration. However, it does yield far less ATP. So now we've produced our 2 pyruvic acids, we've produced our 2 reduced NADs, and we have 2 ATPs as a result of the glycolytic enzymatic pathway. Now what happens is glucose is still needing to be oxidized, and what's going to happen is it's going to enter into the citric acid cycle or the Krebs cycle or the TCA cycle. And the citric acid cycle occurs in the mitochondrial matrix. And this is fueled by the products of glycolysis, such as the pyruvic acid and the fatty acids from fat breakdown. So pyruvic acid must be actively transported into the mitochondria because it's a charged molecule. And then once it's inside the mitochondria, pyruvic acid will enter the transitional phase. So the transitional phase is where each pyruvic acid is going to be converted into acetyl coenzyme A, also known as acetyl-CoA. And this process takes 3 different steps in order for it to occur. The first step is decarboxylation, where 1 carbon from pyruvic acid is being removed, and this produces carbon dioxide gas, which diffuses into the blood to be expelled by the lungs. The second is oxidation. So the remaining 2 carbon fragments are oxidized to acetic acid by the removal of hydrogen atoms, which are picked up by NAD. And the third step is the formation of acetyl-CoA. So the acetic acid combines with coenzyme A to form acetyl-CoA. So then coenzyme A can shuttle its acetic acid to an enzyme in the citric acid cycle that joins it to 4-carbon oxaloacetic acid. And then this produces 6-carbon citric acid. This is why it's called the citric acid cycle. So this is a very complex cycle. I don't need you to know every single step of it, but just know that there are 8 steps, and during these 8 steps, each original acetic acid is decarboxylated and oxidized to different ketoacid intermediates that result in a lot of different complexes. And in the final step of the citric acid cycle, oxaloacetic acid is again regenerated. So what I do want you to know is what we get out of the citric acid cycle. So what do we get out of it? Every time we have a turn of the cycle, we get 2 carbon dioxides from the decarboxylation steps that occur. We also get 4 molecules of reduced enzymes. This includes the 3 NADHs and 1 FADH2. And we also get 1 ATP. And please note that this ATP is produced by substrate level phosphorylation. So let's recap this. So we started with 2 pyruvic acid molecules. So the amount of the final products from 1 glucose molecule is doubled. So what is the outcome? We get 4 carbon dioxides, we get 6 NADHs, we get 2 FADH2s, and 2 ATP. Okay, so we talked about for each turn of the cycle what we get, but again, we started with 2 pyruvic acid molecules. So whatever we get from each turn of the cycle, we have to double. And then adding the products of the transitional phase. The total final products for the breakdown of 1 glucose molecule will be 6 carbon dioxides, 8 NADHs, 2 FADH2s, and 2 ATPs. So wait a minute, where are these other carbon dioxides and these other NADHs coming from? Remember, we have to add the products of what we got in the transitional phase to the total final products of the breakdown. So here we're going to add the 2 carbon dioxide molecules and the 2 NADH molecules. So the final will get 6 carbon dioxides, 8 NADH plus a hydrogen ion, 2 FADH2s, and 2 ATPs. So what's the whole purpose of this, and why do we even need these enzymes to be oxidized and reduced in the fashion that we do? Well, NADH must be oxidized to ensure that there's plenty of NAD available so that glycolysis, the transitional phase, and the citric acid cycle can continue. And the NADH will be oxidized in the electron transport chain. The breakdown products of fats and proteins can also enter the citric acid cycle at certain points to be further broken down. And also different cycle intermediates may be used as building materials for different anabolic reactions rather than just the catabolic reactions which we've talked about. Okay, so now let's discuss the electron transport chain and oxidative phosphorylation. Oxidative phosphorylation consists of two phases. It consists of the electron transport chain and chemiosmosis. First, we're going to focus on the electron transport chain, or the ETC. So basically what happens here is there's a proton gradient that becomes created across the mitochondrial membrane that uses high energy electrons removed from hydrogen atoms from food sources. And please note that the electron transport chain is the only pathway that directly uses oxygen. Take into consideration that the citric acid cycle will not run if oxygen is not present, but it does not directly use oxygen. The electron transport chain is the only pathway that directly uses oxygen. So what's going on here? So NADH and hydrogen ions and FADH2 that are formed from the Krebs cycle and glycolysis are going to be delivering hydrogen atoms taken from glucose to the electron transport chain proteins. The ETC will then use the energy harnessed in electrons of hydrogen to pump hydrogen ions across the membrane to create a proton gradient. Some hydrogen ions will combine with oxygen molecules to produce water. So the electron transport chain harvests energy of food fuels a little bit at a time in order to avoid cellular damage. If it's taking in too much at one time, it can cause the cell to become overwhelmed, and the cell could swell and undergo blebbing and basically implode on itself. So the ETC harvests energy from food only a little bit at a time to avoid this catastrophic damage from occurring. So the ETC involves a chain of carrier proteins, and these carrier proteins are located on the inner mitochondrial membrane, and the inner mitochondrial membrane contains metal atoms or cofactors. There are a lot of different cofactors. I don't need you to know them all, but some of them include the flavins, the cytochromes, and the respiratory enzyme complexes. What I do want you to know is the steps that are involved in the electron transport chain. There are three major steps. So in step 1, complexes 1 and 2 are going to accept hydrogen from NADH and FADH2. And what that does, that allows the NAD and the FAD to be able to return to glycolysis and Krebs cycle and undergo a new cycle of both glycolysis and the Krebs cycle. In step 2, the hydrogen atoms are split into protons and electrons. Then what's going to happen to the electrons is they are going to be passed down the electron transport chain. Each complex is going to be reduced when it accepts an electron, and then it becomes oxidized when it takes that accepted electron and passes it on to the next complex. And please note that coenzyme Q and cytochrome C are what are responsible for shuttling the electrons between the complexes. So in step 2, there's a little bit of energy from the electrons that's going to be released with each transfer. And the energy released is used by complexes 1, 3, and 4 to pump hydrogen ions out into the intermembrane space of the mitochondria. And as this occurs, this creates a hydrogen ion concentration gradient. And then at step 3, at complex 4, the electron pairs will combine with some hydrogen ions and a molecule of oxygen to form water. So the electron transport chain can be broken down, as I said, into two phases. We've hit most of phase 1, and there's just a few other things I want you all to know. So the electrons in phase 1 during the electron transport chain, they're cascading downhill from NADH and a hydrogen ion to progressively lower energy levels until they're finally delivered to oxygen. Energy from electrons is used to pump hydrogen ions into the inner membrane space, and again, this creates an electrochemical proton gradient. The proton gradient has potential energy, which will now be harnessed to do work. The next phase, or phase 2, is known as chemiosmosis. So what's going on here is the proton concentration gradient that was formed also creates a pH gradient and a voltage gradient across the membrane. So hydrogen ions are attracted to the matrix side of the membrane because of all these gradients, but the membrane is impermeable to hydrogen ions. So hydrogen ions can re-enter the matrix only through a mitochondrial membrane channel protein called ATP synthase. ATP synthase is also known as complex 5. So this is a small rotary motor basically that drives the addition of an inorganic phosphate to ADP, creating ATP. So what's actually going on in chemiosmosis? There's 4 steps to the production of ATP. So first, the hydrogen ions flow down gradients through the stationary stator of ATP synthase. As they pass the rotor mechanism, they bind to one subunit, causing it to change shape, and also it causes it to spin. Spinning the rotor turns the connecting rod, and as the rod spins, it activates catalytic sites on the knob that join the phosphate groups to ADP, forming ATP. So ATP is adenosine triphosphate, ADP is adenosine diphosphate. When you add the phosphate group to ADP, you're adding 2 plus 1, so you make 3. So ADP plus a phosphate group will now turn into ATP. Cyanide gas was one of the toxic chemicals that was used in the Iran-Iraq war in the 1980s, which resulted in the deaths of thousands of people. So how cyanide gas actually works is it disrupts oxidative phosphorylation by binding to cytochrome oxidase, and this blocks the electron flow from complex 4 to oxygen. And poisons called uncouplers abolish the proton gradient by making the inner mitochondrial membrane permeable to hydrogen. So hydrogen ions can cross the membrane and can cause systemic damage. Although the electron transport chain continues to deliver electrons to oxygen at a furious pace and oxygen consumption rises, no ATP is made as the uncouplers abolish the proton gradient across the inner mitochondrial membrane. So when we're just sitting around resting, studying, we use about 100 kilocalories of energy per hour. This is equivalent to 116 watts, which is slightly more than the amount that a light bulb uses. And this demand places a huge internal demand on the mitochondria to produce energy. And of the 686 kilocalories in 1 mole of glucose, approximately 262 kilocalories are captured in ATP, and the rest are lost as heat. So this translates as a 38% efficiency in usage of our available fuel. So we are more efficient than most man-made machines, as machines are only about 10 to 30% efficient in harnessing the energy produced and having an energetic output. Let's recap on what we've just learned about the energy yield during cellular respiration. So let's start by talking about how energy flows. So energy is from our food. We consume our food and we utilize glucose in our food. Glucose is then turned into NADH and hydrogen ions. Those molecules are then used in the electron transport chain. They're transported down a gradient and they make a proton gradient energy. And the end product they produce is known as ATP, or adenosine triphosphate. So the net energy gain from complete oxidation of one glucose molecule is a total of approximately 32 ATPs. However, we're not completely certain on the final total. However, if I ask on the test how many ATPs are produced from 1 round of cellular respiration, the answer is 32. So how do we get this number? From substrate level phosphorylation, 4 ATPs are produced. Remember, there's 2 from glycolysis and then 2 from the citric acid cycle. From oxidative phosphorylation, there's 28 ATPs. So the totals between the substrate level phosphorylation and oxidative phosphorylation equals 32 ATPs. However, please remember that energy is required to move the NADH and hydrogen complexes generated during glycolysis into the mitochondria, which uses up 2 ATPs. So the final is actually 30 ATPs that are produced. So there's still debate on whether there's 30 or 32. However, the total end product, when you add substrate level phosphorylation plus oxidative phosphorylation, is 32, and 32 is the answer I'm going to look for on the exam. So cells don't have the capability to store large amounts of ATP, and rising intracellular levels of ATP inhibit glucose catabolism and promote glycogen or fat formation. So now we're going to move into the process of glycogenesis, or the creation of glycogen. So glycogen can be formed whenever there's excess glucose present, and this pathway is catalyzed by the enzyme glycogen synthase. That will be a test question. I will ask, what is the enzymatic catalyst of glycogenesis? And the answer is glycogen synthase. So in glycogenesis, glucose is converted to glucose 6-phosphate and then converted to the isomer glucose 1-phosphate. The terminal phosphate is removed as the enzyme catalyzes the attachment of glucose to the growing chain. And glycogenesis mostly occurs in the liver and in skeletal muscle cells. Now, if you direct your attention to the right-hand side of the screen, let's talk about glycogenolysis. So this is the breakdown of glycogen using glycogen phosphorylase, and this happens when there is a low presence of glucose in the blood. So glycogen phosphorylase splits and phosphorylates the terminal glucose on glycogen, and this forms glucose 1-phosphate, which is converted to glucose 6-phosphate, which then can enter glycolysis in that particular cell. So liver cells, as well as some kidney and intestinal cells, also contain the enzyme glucose 6-phosphatase that removes the terminal phosphate. And by removing the terminal phosphate, that produces free glucose. As the glucose molecule is free, it can now enter the bloodstream and be used by other cell types. This slide is a summary of the different carbohydrate reactions, and the only one that we haven't talked about yet is gluconeogenesis. So gluconeogenesis is the process of forming new glucose, hence the name neo, from non-carbohydrate sources. And gluconeogenesis primarily occurs in the liver, where glucose can be formed from glycerol and other amino acids when the blood glucose levels drop below normal. When blood glucose levels drop below normal, this can induce a state known as hypoglycemia. And gluconeogenesis is a very important process as it protects against the damaging effects of hypoglycemia, and it's especially important for our nervous system. So now we're going to move away from talking about glucose and glycogen and talk about lipid or fat metabolism. So lipids provide a greater energetic yield than glucose or protein catabolism does. Lipid catabolism yields 9 kilocalories per gram versus the 4 kilocalories per gram from carbohydrate or protein catabolism. And most of the products of fat digestion are transported in the lymph as chylomicrons. Only triglycerides are routinely oxidized for energy, and there are 2 building blocks of triglycerides which are both oxidized separately. So we're going to talk about glycerol breakdown and fatty acid breakdown. So let me direct your attention to the left side of the screen and follow me as we talk about the glycerol breakdown. So glycerol is broken down into glyceraldehyde 3-phosphate. This is the same as what happens in glycolysis. And then this allows for entry into the citric acid cycle after being converted into pyruvic acid and acetyl-CoA. So the ATP yield is roughly half that of glucose because glyceraldehyde is only half of a glucose molecule. So this process only yields 15 ATP per glycerol. Now let me redirect your attention to the right side of the screen and let's talk about fatty acid breakdown. So fatty acids undergo a breakdown process known as beta oxidation in the mitochondria. And the fatty acid chains are broken down into 2 carbon acetic acid fragments. And the coenzymes FAD and NAD are reduced in this process. The acetic acid fragment fuses with CoA to form acetyl-CoA, which then enters the citric acid cycle. So the reduced coenzymes, the FAD and the NAD, can enter the electron transport chain. And this process is referred to as beta oxidation because 2 carbons are broken off the fatty acid chain and allows for a 3rd position carbon to become oxidized. Lipogenesis, or the creation of fats, is a process of triglyceride synthesis that occurs when cellular ATP and glucose levels are high. Dietary glycerol and fatty acids not needed for energy are stored in the form of triglycerides. 50% of them are stored in our adipose tissue, and the other 50% are deposited in other areas. Glucose is easily converted to fat because acetyl-CoA is an intermediate in glucose catabolism, and it is also the starting point for fatty acid synthesis. So lipolysis, this is the breakdown of stored fats into glycerol and fatty acids. It's the reverse of lipogenesis. Fatty acids are actually preferred by the liver, the cardiac muscle, and resting skeletal muscle as a main fuel source. Lipolysis is accelerated when carbohydrate intake is inadequate. And beta oxidation of the released fatty acids results in production of large amounts of acetyl-CoA. Acetyl-CoA can enter the citric acid cycle only if enough intermediates, such as oxaloacetic acid, are available. If the intermediates are not available, then acetyl-CoA can accumulate. And accumulated acetyl-CoA can be converted by ketogenesis in the liver to ketone bodies, also known as ketones. And the ketone bodies include acetoacetic acid, beta-hydroxybutyric acid, and acetone. If we accumulate too many ketone bodies in our blood, this can lead to a state known as ketosis. Ketosis is very common in starvation, unwise dieting, and diabetes mellitus. Ketone bodies are also excreted in the urine. Ketones are acidic, so a buildup of these molecules can lead to metabolic acidosis, which can cause dangerously low pH levels. And the patient's breath can smell fruity from the vaporizing acetone that's present. Also, the patient's breathing becomes rapid as the lungs try to release carbon dioxide in order to raise the systemic pH level.